Hi, my presentation today is about real-time 3D target inference via biomechanical simulation. We are trying to explore an intriguing question. Can we synthesize realistic user movement without involving real people? This talk will present how we can replicate human data collection via simulations and how we can use this simulation to enhance actual users' interactions in virtual reality. Input techniques in virtual reality have seen long-term improvement. For instance, raycasting is an intuitive method for selecting distant targets by controlling a ray emanating from a controller. However, selecting targets in virtual reality faces some challenges, especially when the targets are densely arranged. It is mainly due to imprecise control. This imprecision often comes from human motor noise and the sensor limitations of devices. Another source of error is the Heisenberg effect, which happens when pressing a button shifts the controller's orientation, which affects accurate control. One of the practical solutions utilize user movement to infer the user's intention and correct the user's imprecise input. This can be achieved through a neural network model trained in a supervised manner with a human dataset. However, this involves the expensive process of collecting training datasets from human users. One major issue is that many trained models depend heavily on their training datasets. This means that if we consider new target environment, configurations, or interactions with newly developed devices, it will require training the model with a new dataset. Therefore, it is necessary to collect new data from the beginning each time. This will lead us back to the intriguing question that I raised. How about generating realistic movement data of users without involving actual users? If we had a simulated user capable of generating diverse motion data with human-like biomechanics for every new target configuration or new interactions, it could significantly reduce the cost associated with traditional human data collection. The main contribution of this work is our newly proposed simulation-based inference method for inferring a user's selection target in virtual reality. In simpler terms, we've developed a simulated agent to mimic humans' input motion and utilize this simulated data to infer an actual user's intentions. Our work progresses through three steps. First, we built an agent that simulates human actions based on biomechanics. Next, we developed an inference model based on the agent simulation. Finally, we deployed this inference model to assist end users in virtual reality. And each of these steps has been validated by our separate studies. In the simulation step, our foundational assumption is that humans behave rationally within our perceptual and motor limitations. Under this premise, we created an agent with human-like perception and motor abilities. So in this simulation, a virtual agent with human limb kinematics selects targets using the same raycasting mechanism in virtual reality. The agent perceives the given target selection task through visual perception from its eyes and proprioception from its biomechanics. Its internal control policy then decides on an action based on these observations. These actions directly actuate the joint and determine when to click for selection. By rewarding and penalizing the agent's actions based on task performance, we optimize its action policy through reinforcement learning. Putting together, we mimic human behavior by an agent with rational decision-making and a human-like perceptual and motor process. We also accounted for motor variability that is present within individual human users or across different users. To simulate intra-user variability, we introduced posture shifts in each trial and noise on motor actuations. For inter-user variability, we varied a human agent's limb sizes, motor noise, and reward weight to represent different types of users. These characteristics are randomly sampled in each episode, training the agent to simulate a range of users with appropriate variability. One of the key advantages of this simulation approach is its transferability. Once the training environment is established, introducing new target environment just requires retraining an agent. This eliminates the need for expensive human data collection. In the next step, we leveraged those simulated data to create an inference network. This network predicts a user's intended targets by observing their prior movement. Our goal here is more than just finding discrete targets. Instead, we estimate the positional posterior distribution of targets. We use the type of neural network called normalizing flows to estimate this sophisticated distribution quickly, achieving real-time speeds of under 10 milliseconds. Here, the entire training process utilized only the simulated data from our agent. This probabilistic method can quantify the uncertainty of our inferences. For example, initially, uncertainty in users' intentions will result in a wide posterior distribution. But as the episode progresses, this distribution becomes more focused. With this distribution, we also can compute the confidence level in our inferred target, which can serve as a measure of result reliability. In the final step, we deployed our inference model on actual VR devices to assist users in selecting targets. We implemented a mechanism where the ray sticks toward the inferred target in real time if the confidence is high. This allows users to make selections with visual assistance toward the inferred target. This confidence-based approach can provide more robust assistance by managing each uncertainty. Traditional heuristic methods like nearest neighbor suggestions offer constant system intervention, which can sometimes impede user performance through inaccurate suggestions. Our inference model, however, minimizes such errors by relying on internally measured confidence levels. Furthermore, the outcomes of the model, both the inferred target and the confidence level, offer designers a range of assistance options that they can build. For example, we showed that more proactive system interventions are feasible, such as an autoclick feature of the system that automatically selects a target when the confidence is sufficiently high. We demonstrated this assistance method could further speed up the user's input process. Our three separate studies validated each step of our work: simulation, inference, and assistance. For instance, our simulator demonstrated target selection performance similar to that of human users with similar levels of motor variability. Here, I'd like to go into more detail about some of our interesting findings from those studies. In validating the performance of our simulation-based inference, we found that our inference accuracy level nearly matches an inference network which was trained with actual human data, but it was slightly underperforming. However, it's important to note that the performance of human data-based methods depends on the volume of the training data. Our findings indicated a decrease in inference accuracy with lesser amounts of human user data. Importantly, our simulation-based inference outperformed the human data-driven approach when it was trained with data from fewer than 7 human participants. In the next validation on our assistance, we saw that user input performance improved in both speed and accuracy. Interestingly, in scenarios with easier selections, our performance improvement was actually at similar levels to previous methods. However, in more challenging selection scenarios, our method significantly improved user selection accuracy over traditional heuristics. This highlights the effectiveness of using confidence levels to minimize incorrect interventions. It turned out effective, especially in scenarios needing precise input. The main takeaway from our work is that we've demonstrated a method of using simulated data to enhance real user interactions. We've proven that biomechanical simulation can accurately mimic human motor variability in input interactions. Then, we've shown that simulation-based inference matches the performance of a human data-driven approach with data from 7 users. Lastly, our inference method provides robust options for selection assistance. I hope you enjoyed this talk. Thank you for listening.